In the previous lecture, we discussed about the properties of signals like periodicity and signals being even signals or odd signals, and we did some examples as well. And in today's lecture, we are going to talk about the transformations of the independent variable. Now, first of all, what do we mean by the independent variable? And then we'll see what are the different transformations available and how to perform those transformations in this lecture. So what we are seeing here on our screen is a continuous time signal x of t, and at the bottom is a discrete time signal x of n. Now, the independent variable is the parameter that is on the x-axis. So in the case of the continuous time signal, in the context of this course, more often than not, it's going to be time. It can be any other variable as well, but we are, in this course, we'll be dealing with the independent variable as time. But in general, whatever is the parameter that lies on the x-axis, that is referred to as the independent variable. And whatever is the function that is representing the y-axis, or that is being represented on the y-axis, is called as the dependent variable. So x-axis variable is the independent variable, and the y-axis function that we have, that's the dependent variable. Similarly, in the discrete case, the index n that we have on the x-axis, that is our independent variable, and the function that we have on the y-axis, that is our dependent variable. So in general, the independent variable is the parameter that lies on the x-axis, and the dependent variable is the parameter that lies on the y-axis. So from these examples, here we have time as our independent variable, and here we have the index number n as our independent variable. So this t here, let me mark that. So that t here is our independent variable, and the n here is our independent variable. Now it becomes useful to transform the independent variable in various ways for analyzing the signal, or even to analyze and study systems, and we will see how they can be used later on. But today we are going to focus on what are the transformations that are available to us and how to perform those transformations. And later on in the latter part of this course, you will see how these transformations can be used to study and understand signals and systems. And you will see that how useful these transformations are in order to analyze signals as well as systems in this course, and in the study of signal processing in general, or in the study of signals and systems in general. Okay, so first of all, what are the different transformations that are available? There are three different transformations that can be done on the independent variable, and we will study each of those transformations one by one, and later on we'll see how to put these transformations together. So we will see the transformations individually, and then typically when we analyze signals or systems, we may have to perform these transformations, all the three transformations to the signal, and there is a systematic way of doing it. If there are multiple transformations that need to be performed to a particular signal or to a system, then there is a systematic way of doing that. So we will see what that systematic way as well is. Okay, so the first transformation that we can perform on the independent variable is called as time shifting. So the first transformation is time shifting. Now, whether we are dealing with the continuous time signal or the discrete time signal, it is still referred to as time shifting. And time shifting basically means shifting the signal either to the left or to the right without affecting its shape or scale. So simply the waveform will be shifted either to the left or to the right. That shifting is called as the time shifting, because the waveform is going to be shifted in the horizontal direction along the axis of the independent variable. So in the continuous case, it is shifted along the axis of the time variable, and in the discrete case it is shifted along the axis of the index variable n. So it is a horizontal shift of the waveform by a certain amount. The shift can be either to the right or to the left. Okay, so the first transformation of the independent variable that we can perform is called as time shifting, and the second transformation that can be performed for the independent variable is called as time reversal. Now, time reversal is basically indicating that the axis of the independent variable is going to be reversed. So normally we have the origin in the center, and the time to the right of the center is the positive time axis, and to the left is the negative time axis. But in time reversal, we're just going to rotate this time axis by 180 degrees, so that the positive time axis goes to the left hand side and the negative time axis comes to the right hand side. Or in other words, it is as if looking at the signal not from the top of the screen, from behind the screen. So if you are on the other side of the screen now and looking at this waveform from behind it, you will see this positive thing on your left hand side rather than on the right hand side, right? So this will look like the positive is on the left side and the negative is time is on the right side, and you will see the entire waveform. If you're looking at it from behind the screen, you will see this entire waveform is reversed. So what is on the left hand side here, you will see on your right hand side, and what is on the right hand side here, you'll see it on your left hand side if you're seeing it from behind the screen. So that is what we call as time reversal, and the same thing applies for the discrete signal as well. So it's basically rotating this axis by 180 degrees. So it's just rotating like this, so that the positive n goes on the left hand side and the negative n comes to the right hand side, or equivalently it's as if you're looking at the signal from behind it. Okay, as if you go behind. So you're watching it from the top of the screen now. So when you go behind this signal and so look at it from behind it, the way you see the signal, that is basically a time reversed version of the signal. So we want to depict it and reverse the time. Okay, so that's one other transformation of the independent variable. And the third transformation that can be performed for the independent variable is called as time scaling. Okay, and in time scaling, we are basically going to multiply the time parameter with some constant. So the signal will either get compressed, that is, the shape will remain the same, but the duration of the signal may become expanded, or it may become shorter, but the shape will remain the same. So we are either going to compress the signal or expand the signal. So that is called as time scaling. So basically, if you want to represent these operations mathematically, time shifting is x of t is our original signal. Shifting means shifting it by some amount t naught. Now, depending on whether this t naught is positive or negative, so if this t naught is positive, if the value of t naught is positive, then we'll get x of t minus t naught. That means the waveform is going to be shifted to the right. If this t naught is a negative number, then it will become x of t minus that t naught, right? So minus of minus will become plus, so x of t plus t naught. So when t naught is negative, this whole argument here will become t plus t naught, in which case it is equivalent to shifting this waveform to the left. Similarly, time reversal is basically saying x of minus t. So whatever is x of t, we are going to reverse the time by putting minus t in place of t. So basically the time axis is going to be reversed. So it's like rotating this time axis about the origin, so that the positive t comes to the left hand side and the negative t will become will come on the right hand side. So that's basically the mathematical representation for time reversal. And time scaling is x of some constant a into t. So where a is a constant right? So we are going to multiply the time variable with some constant, with some number. So depending on whether that number is greater than 1 or less than 1, the signal will either be shortened in its duration, or expanded, or elongated. Or so if it is greater than 1, it will be elongated. Sorry, if it is greater than 1, it will be shortened, and if it is less than 1, the signal will be elongated. Okay, so we are going to look at the examples of how to perform these transformations. And first of all, you see the examples of performing these transformations one by one. And we will see how the shift, or this reversal, or the scaling is taking place. And at the towards the end of the lecture, we will work out an example of performing these transformations together, if there is a shift, a reversal, as well as a scaling involved in a transformation. Okay, so we will now see how these transformations are performed one by one. So we'll first look at the time shifting aspect, the time shifting transformation, and then we'll see the time reversal, and finally we'll also look at the time scaling operation as well. And we will see all of these for the discrete case as well as for the continuous case. And I will show you the example for time scaling only for the continuous case, but the similar thing applies for the discrete case as well. And then at the end, we will work out an example. So the first operation that we are going to see is the time shift for the discrete signal. So we have our original signal here, x of n, okay, and that's a discrete signal. And if you notice the origin, 0, at the origin you have this first signal which is at its peak value, after which it's constant, and then it starts decreasing. So the origin is here. Now the signal that we have at the bottom, that is the shifted version of the same signal, and now you see that this has been shifted to the right. So this waveform has been shifted to the right by a certain amount. So let me draw that in a different color. So by shifting it by a certain amount and not so that is what gives us the signal at the bottom. So instead of this first highest value being at 0, now this entire sequence has been shifted to the right, such that this first maximum value that you have at 0 here, that has now come to that n naught, whatever is that shift n naught. So suppose this n naught is equal to 5. So instead of 0, it will be shifted to the right and it will come at 5. If this is 10, then it will come at 10, and so on. So whatever is that number, it will come, that shift amount, it will be shifted to the right by that n naught. Suppose this n naught was negative, then x of n minus n naught will become x of n plus n naught, in which case this whole waveform would have been shifted to the left by that n naught, so that this first maximum value would be somewhere here at minus n naught. Okay, so time shift, it shifts the signal, along the x-axis. Okay, so when we say x of n minus n naught, it shifts the signal along the x-axis by an amount n naught. That's the first property. Now the second property is that if n naught is positive, that is n naught greater than 0, then the shift is towards the right. Shift is to the right by an amount n naught. And if n naught is negative, if n naught is negative, meaning n naught less than 0, then the shift is to the left by an amount n naught. Okay, so what we have depicted here in this plot is a shift x of n minus n naught for n naught greater than 0, because this waveform is shifted to the right by an amount n naught. So 0 has come towards n naught. So this is a depiction for n naught greater than 0. Okay, that is why the origin has from 0, the value that was at the origin, that has got shifted to the right and it is now on n naught. If it was less than 0, that would be centered on minus n naught. Okay, so basically the way to see it is when you have a certain shift by an amount n naught, so when you have it as x of n minus n naught, when you compare it with x of n, whatever is at 0, that will move to n minus n naught equal to 0. So it's when you say when you take this index, okay, when you take this index n minus n naught and make it equal to 0, n minus n naught equal to 0, that means n becomes equal to n naught, right? So basically this is having a certain value at the origin. So whatever is at the origin, that will go to n naught. So in this case, so the whatever is at 0 here, that has now come to n naught. So similarly, when we have x of n plus n naught, so when we have it as x of n plus n naught, then if you take this argument and make it as equal to 0, so if you make n plus n naught equal to 0, so that is basically saying n naught n equal to minus n naught, right? So whatever is at the origin will go to minus n naught. So if it is n plus n naught, the origin will go to minus n naught, so that means the waveform will be shifted to the left. So that's how you would remember which version is the right shift and which version is the left shift. So basically put this term what's inside the brackets and make it equal to 0, and when you see n equal to n naught, then that n naught is positive now here. So in that case, whatever is the origin that comes to n naught, so that corresponds to a right shift. Now when you make this as 0, n becomes minus n naught, so that means whatever is the origin that goes to minus n naught, so that means the origin is shifted to the to the left, right? So that's how you would remember whether the shift is taking place to the right or to the left. So whenever we have it as n minus n naught, it is shifted to the right, and whenever we have it as n plus n naught, that means it is a shift towards the left. Similarly, if it's a continuous time signal, if it is t minus t naught, it is a right shift. If it is t plus t naught, it is a left shift. Now generally we will write the notation as n minus n naught or t minus t naught, and simply say if n naught is positive, it is a right shift. If n naught is negative, it is a left shift. Okay, so we have seen the time shift transformation for the discrete signal. Let us have a look at it for the continuous time case as well. So we have here a signal x of t and a shifted version here. Now you notice the wave shape is the same here as what is on the top, except that it has been shifted to the left by a certain amount. So this corresponds to this t naught being less than 0, because the waveform has been shifted to the left. So when the waveform is shifted to the left, that means it is t plus t naught, right? Now this is t minus t naught for t naught less than 0, that is t naught is negative. So when t naught is negative, that means t minus t naught, so t plus t naught. Okay, so the example that is depicted here is for the case where t naught is negative. So like in the discrete case, here also x of t minus t naught, x of t minus t naught is shifted version of x of t. So when t naught is positive, the shift is to the right, so it's a right shift by t naught. When t naught is negative, that is less than 0, then it is left shift by an amount t naught. Okay, so the amount of shift is given by this value of t naught, and the direction of the shift depends on the value of t naught. So here the shift that is shown here is for the case of x of t minus t naught when t naught is less than 0. So this is t naught is less than 0, that is negative. So when t naught is negative, x of t minus t naught is basically x of t minus t naught, all right, which is simply x of t minus of minus is plus t naught, because t naught is a negative number. So whenever we have a plus, that indicates a shift to the left, and whenever we have a minus, that indicates a shift to the right. The general notation is simply t minus t naught, and when this t naught is positive, we will have it as t minus t naught, and when this is negative, it will become t plus t naught as it has been depicted here. So again, if we just make this argument, t plus t naught equal to 0, so if I make this as t plus t naught equal to 0, basically we are saying t is equal to minus t naught. So the time axis origin, which is here, it has got now shifted to minus t naught. So the value that you have at the origin, so this peak here, that has come to minus t naught. So it has got shifted to the left. So if that is the origin, that corresponds to minus t naught, right? So it is shifted to the left by an amount t naught, so that is 0. Again, what is depicted here is just the amount of shift t naught, okay, and it says t naught is negative. So if you plot the origin value as 0, then that will become minus t naught, okay. So you have to be very clear in your understanding of this. So the origin has basically what was at 0 now, that has come at minus t naught, because when you make this argument as equal to 0, you get as t equal to minus t naught. So 0 will become minus t naught. So the point that you had at 0, that has now come to minus t naught. So that is a shift to the left, okay. So that's the example for the shift for the continuous signal. The idea is the same for both the discrete case and the continuous case. A time shift basically means shifting the waveform to the right or to the left by a certain amount t naught or an amount n naught in the case of a discrete signal. And if there is a plus here, it is indicating a shift to the left, and if there is a minus here, it is indicating a shift to the right, okay. So we have seen time shift transformation. Next we are going to see the example of a time reversal transformation, and now we have this for the discrete case. And as I said before, time reversal is basically rotating the x-axis by 180 degrees along the y-axis or along the origin. So when you just rotate this line and bring it here, that means the plus n will become minus n, and the minus n which is on the left comes to the plus n. So basically it's like as if looking at the signal from behind the screen. So if you look at the stop signal from behind the screen, you're going to have a view which is similar to the figure on the bottom side, right? So time reversal is basically flipping the time axis. flipping the time axis, or equivalently it is as if viewing the signal from behind. Okay, it's as if viewing the signal from behind. Okay, that's the way you can imagine the time reversal operation. So clearly, if you're looking it from the front of the screen now, we see the signal which is starting from this low amplitude, going to the negative and then coming up here. If you see it from behind the screen, then you're going to have this on your left hand side and this side on your right hand side, right? So when you're viewing from behind, you will see this on your left hand side, which is what you have here, and then this part on your right hand side. So it's this is basically the same signal which is viewed from behind the screen, and that is exactly what is what we mean by time reversal. So this minus n is basically rotating the whole signal by 180 degrees. So it's basically rotating this whole thing by 180 degrees. It's as if you are 180 degrees. Okay, so that's as if viewing the signal from behind. So that's what it means by time reversal. And we have seen now for the discrete case, and similarly we will see for the continuous case as well. So here we have the continuous signal. So what you see is this is the top one is the signal that we are viewing from the front of the screen, and if you had to look at the same signal from behind the screen, then this is what it will look like. So this part which is on the right hand side, that comes to your left hand side now, and what is on your left hand side, that becomes the right hand side. It's as if you're looking at the signal from behind, or equivalently you're looking at its mirror image, right? So the x-axis is going to be flipped. So what is on this side time axis, that has gone to the negative side, and what is on the negative time axis, that has come to the positive side of the time axis now. So x of minus t is basically the time reversed version of the x of the signal x of t. So basically it is rotation by 180 degrees. Okay, when you rotate this by 180 degrees, that is this whole axis is going rotated, then what we get is let me draw it in the same direction as the other one, and we will get this signal which is on the bottom part, and clearly you can imagine it yourself. Okay, what we see on the bottom is basically what you would see for the top signal if you're viewing it from behind. So that is what is called as the time reversal operation. And to give a more practical example of time reversal, it's like let's say you have a music signal or an audio signal, and you're playing it in the correct direction. You're listening to music by playing the music in the correct direction, and time reversal is basically playing the music in the reverse direction and listening it backwards. So it's as if you are, if you have a cassette tape, then it's like rewinding the tape, and while rewinding it, you are listening to the music. So basically it's like listening to the music in the reverse direction, and basically that signal is going to come back in this way, right? So that's exactly what you see in the time reversed version of the signal. And finally, the third transformation that we can perform on a signal is what is called as the time scaling. Now so we have depicted here the signal x of t, which is the original signal, and the two signals which are at the bottom are the scaled versions of x of t. Now this is basically x of a t, some constant a times t, where a is some number okay, some number, and depending on the value of a, what we see is in the time scaling we get the same shape of the waveform, okay, but it is scaled in time. So this, you see, it has become like a compressed version of the original x of t, and at the bottom when you have t by 2, that is an elongated or expanded version of the original x of t, right? So now depending on the value of a, when a is greater than 1, we get a compressed version, and when a is less than 1, in this case a is equal to half, so it's x of a t, so a is equal to 2 here. So for this example, a equals 2, and it is t by 2, that means 1 by 2 times t. So the example here is depicting for a equals half. So when a is greater than 1, the signal is kind of compressed, and when a is less than 1, the signal is elongated. So again, to understand this in a better way, let's take the example of a music signal in a tape, on a magnetic tape, in a cassette. And suppose you have a video or an audio of let's say 1 minute, and if you're playing it at the normal speed, you will get the audio, the music, for the complete 1 minute. If you play it at double the speed, at 2 times the speed, then the 1 minute audio will become half a minute audio, because you have played the tape at twice the speed. So the music will get finished in half the time, so it has become smaller. And if you played that audio tape at a slower rate, say half the speed, then the 1 minute video or audio will become a 2 minute audio, right? So basically the time scaling, if it's basically like playing the signal faster or slower. So if the original signal had a certain duration, if you played out that signal faster, then the signal will be finished in a shorter time. And if you are playing that signal at a slower rate, then you will have that signal playing out for a longer duration of time, right? And that is exactly what we are seeing here. So when a is greater than 1, when a is greater than 1, the scaled signal x of a t is shortened or compressed, but the better word is shortened in length, okay? So on the time axis, let's say this is having an original duration of 10 seconds. Now in this case, from the starting to the end, it will become 1 second, because you have played it at twice the speed. And similarly, when a is less than 1, when the scaling factor a is less than 1, the scale signal x of at is elongated. It is becoming longer, okay? So basically, if you had a 10-second audio, and if the tape was played at a much slower rate, then that music will become longer, right? It's like me speaking at my normal speed, or at a faster speed, or at a slower speed. If I say hello, how are you, that's my normal speed, and to say that sentence, let's say it takes 1 second. If I'm making it faster, hello, how are you, that becomes at a much faster rate, so the same sentence was completed in a smaller time, so the signal has become shortened. And if I said the same thing at a much slower rate, hello, how are you, that has got elongated, so the same sentence has taken a longer amount of time, okay? So it's basically playing out the signal at a faster rate or a slower rate, depending on the value of the scaling factor. So when a is greater than 1, it's basically like playing out the signal at a faster rate, so the signal will become shortened. And when a is less than 1, it is as if playing out the signal at a slower rate, so the signal will become elongated or lengthened, okay? So that's the time scaling transformation of the independent variable. Now, more often than not, we will come across situations where all these three operations would be happening to a particular signal. So, when we have all these three operations together, we can denote that transformation as, say, x of at, or we are going to denote this as alpha t plus beta. Okay, I use the letter a here in this example, but when we are going to combine this together, I'm going to use this letter as alpha. So alpha is the scaling parameter, beta is the shifting parameter, and the time reversal, if alpha is having a minus with it, it will be a scaling along with the time reversal as well. Okay, so if alpha is a positive number, then it is just a scaling. If as alpha is a number with a negative sign in it, so that will make it x of minus alpha t, right? So that will be a scaling as well as a time reversal and some shift. And if this beta, if there is a plus sign here, it means the shift is to the left. If there is a minus sign here, the shift is going to be to the right. And if this alpha is if this value of alpha, or the magnitude of alpha, is greater than 1, then the signal will be shortened. If the magnitude of alpha is less than 1, then the signal will be elongated. And if alpha is positive, then it will have the same time axis, and if alpha is negative, then the time axis will be reversed as well. So depending on the combinations of alpha and beta, we will have time scaling, time reversal, and time shift. So let's summarize them. So first of all, the first case, when alpha is positive, so alpha greater than 0, there is no time reversal. Okay, no time reversal. And when alpha is less than 0, there is time reversal, because when alpha is less than 0, that means there is a negative sign here. It is x of minus alpha t, so that's basically x of alpha times minus t. So when there is a minus with the t variable, there is a time reversal. And similarly, when alpha, or when the magnitude of alpha is greater than 1, so when the magnitude of alpha is greater than 1, it is shortened. And when the magnitude of alpha is less than 1, it is elongated. And when beta is non-zero, let me write it specifically. When beta is, in this example, because we already we have denoted the general form as a plus, so when beta is positive, we will have it as x of alpha t plus beta. So when we have it as plus beta, it is a left shift. And when beta is less than 0, it will be a right shift. Okay, so that's all the transformations we are going to have. And when you have these transformations together, okay, for a particular signal, we will always, the general rule, the proper way of doing it is, we have to first perform the shift and then perform the scaling and reversal. Okay, so never perform the scaling part first and then perform the shift. That will cause a bit of confusion. Okay, as I will show with an example as well. The proper way of doing it is first shift it to the left or to the right, and then perform the time reversal and the time scaling operation. So when we have all these operations together, the sequence in which we will do it is, first the shift and then the scaling. Okay, now let's have a look at an example and work out all these transformations of the signal, and we will see what is the effect and how to perform these transformations. So here we have an example of a signal in the continuous time x of t, okay, and the signal has been chosen in a specific way so that we can see what happens with the operations. Okay, so you see that at 0 it is changing from 0 to a value of 1, so the y-axis value here is 1, and it remains 1 from 0 up to 1 on for time axis value 1. So the x-axis is variable is time, that's our independent variable. So the signal is having a value of 0 until t equal to 0. At t equal to 0 it changes to 1, it remains at 1 until t equal to 1, and from t equal to 1 to t equal to 2 it gradually decreases like this and becomes 0 at t equal to 2, and beyond t equal to 2 it is continuing to be 0. So that's our original signal x of t. Now we are going to see some time scaling operation, time shifting operation first on this. So let's do time shift here. So with the time shift operation, we are going to do x of t plus t naught. Now I'm going to set the value of t naught to be equal to 1. So it is x of t plus 1. So that is x of t plus t naught. And in our general notation, we had written it as t minus t naught. With when t naught is negative, it becomes t plus t naught, right? So with t naught equal to, that's basically t naught equal to minus 1. Okay, so let me write in the general form. It's x of t minus t naught with t naught equal to minus 1. So when you put in place of t naught as minus 1, say it's t minus of minus 1, which is t plus 1. So when we have a shift which is denoted with a plus inside this bracket, okay, t plus 1, it's basically shifting the signal to the left by an amount 1. So what is happening at 0, the same thing will happen at minus 1. And what is happening at 1, that will get shifted to the left by an amount 1. So 1 will come to 0. And what is at 2, that will get shifted by an amount 1. So when you shift 2 by an amount 1, 2 will become 1, and so on, right? So all these transformations or changes in the signal that are happening in the original signal at whatever time, they will all move to the left by an amount 1. So what is happening at 0, that will come to minus 1. Whatever is happening at 1, that will come to 0. And what is happening at 2, that will come to 1. So they're all moving to the left. Because we have a plus here, so it's a because there is a plus here, so that indicates a left shift by 1. So we are shifting this entire signal to the left by an amount 1, in which case let's mark the axis values. So now the axis values are still 0, that's 1, so that's 2, that's minus 1, that's minus 2, and so on. So whatever has been happening at 0, that will happen at 1. That is going to happen at minus 1. So the signal is going to look like this. So it starts from somewhere, and up to minus 1, it's going to be a constant value of 0. At minus 1, it is going to make this transformation. So what was happening at 0, that will be shifted to the left by 1. So that will come here, and it will remain at that value till here. So whatever was happening at 1, that is this gradual descent, okay, which started at 1 and ended at 2, that will get shifted to the left by 1. So that when it comes to the left here, it will come at 0. So at this place it will start, and this 2 will get shifted to the left at by 1. So we'll have this from here to 1, and then the constant will continue. The what was happening at 2, that will continue at 1. So we see that this is basically the signal on the top shifted to the left by an amount of 1. Okay, so the y-axis value, the peak value here is 1 as before. So just the only change that has happened in this transformation is that the signal which is on the top has got shifted to the left by an amount 1. Similarly, let's see what if this t naught is positive in this x of t minus t naught. Then we will have it as x of t minus 1. That means this whole signal will be shifted to the right by an amount 1. So let's work out that example as well. So what we have on the top here is the same signal as in the previous case, but now we are going to shift it by x of t minus t naught for t naught equal to plus 1. So t naught is now positive, so that gives us x of t minus 1. So when there's a minus here, it indicates that the waveform is shifted to the right by an amount 1. So whatever is at 0, that will come at 1. So what will happen is the signal is going to be constant up to 1, and it was going up at 0, so that going upward, that this vertical line will come at 1, will get shifted from 0, it will get shifted to 1. So it is shifted to the right by an amount 1, and then from 1 to 2 it will remain constant. It was constant at 1 from 0 to 1. This whole thing will get shifted to the right, so it will be from 1 to 2, and from 2 to 3 it will have a gradual descent like this, because it was happening at 1 and ending at 2, this gradual descent, right? So that will get shifted to the right by 1, so it will start at 2 and end at 3. So in this case, the signal is going to start from somewhere here and be constant up to 1. Okay, so it was originally constant at having a value of 0 up to 0. Now that is getting shifted to the right by 1, so it was getting shifted to the right by 1, and the vertical line which was at 0, that has moved to the right by 1, so we'll get it at 1. So this vertical line comes here, and then from in the original signal from 0 to 1 it was constant, because this whole thing is getting shifted to the right by 1, so that constant part will now be from 1 to 2, and then the gradual transition which was taking place from 1 in the original signal, that will get shifted to the right by 1. So it is going to have that transition starting from 2 and ending at 3. So it will be something like this. Let me draw this properly. So it exactly ends at 2, and then it is going to have this gradual thing from up to 3, and then after 3 is going to be constant like this. Okay, so this is the right shifted version of the original signal, and it is right shifted because we have a minus here. Okay, when there is a plus in the transformation here, then it's a left shift. When there is a minus here, it's a right shift. So we have seen the time scaling operation for this. Not the time scaling operation, but rather the time shifting operation. So basically we have done shifting to the left and to the right. So this is a right shifted version of x of t. So x of t minus 1. So x of t minus 1 is x of t shifted to the right by 1. Okay, when there is a plus here, x of t plus 1 is basically x of t shifted to the left by 1. Okay, so we have seen the time shifting operation for this particular example. Okay, I'm going to stop here, and I will continue with the time scaling as well as the time reversal operations in the next lecture. So in the next lecture I will start with the same example and just quickly recall the time scaling operation, and then in detail explain the time reversal and also the time scaling operations. Okay, and the important thing to note here is that when we have all these operations to be performed together, we will do the shifting first and then perform the scaling and reversal, and that would be the proper way of performing the transformation. Okay, and in the next lecture I will show you how to perform these, and we will continue with those topics in the next lecture. I'm going to stop here. We will meet again in the next lecture.